Picture this. Right now, as you're watching this video, there might be another being on a distant world doing the exact same thing, wondering if they're alone in this vast cosmic ocean. For thousands of years, humans have gazed up at the night sky and asked one fundamental question that has haunted our species. Are we alone? But here's what's incredible. We're no longer just wondering. We're actively hunting for the answer, and we're getting remarkably close to finding it. What if I told you that in the past 3 decades, we've discovered over 5,000 worlds orbiting distant stars? What if I told you that some of these worlds might be harboring life right now? And what if I told you that within your lifetime, we might finally answer that age-old question that has defined human curiosity since the dawn of consciousness? Today, we're embarking on humanity's greatest detective story, the search for exoplanets, and the profound implications of what we might find. This isn't just about distant rocks floating in space. This is about potentially discovering that we're part of a cosmic community we never knew existed. Before we dive deep into this incredible journey, I'm curious, where in the world are you watching this from right now? Drop a comment below and let me know your location and what time it is where you are. I love connecting with fellow space enthusiasts from around the globe, and it's fascinating to think that while we're all looking up at the same stars, we're seeing them from completely different perspectives on our pale blue dot. The cosmic lottery, understanding the scale. Let's start with a number that will fundamentally change how you think about our place in the universe. Are you ready? In our observable universe alone, there are approximately 2 trillion galaxies. Each galaxy contains, on average, 100 billion stars. That means we're looking at roughly 200 sextillion stars. That's a 2 followed by 23 zeros. To put that in perspective, there are more stars in the universe than there are grains of sand on every beach on Earth. But here's where it gets even more mind-bending. Recent studies suggest that, on average, every star hosts at least one planet. Some have multiple planetary systems, while others might have none, but the average works out to about 1 planet per star. This means we're potentially looking at 200 sextillion planets scattered throughout the cosmos. Now, let's play a cosmic lottery game. Even if we're incredibly conservative, and say that only 1 in a billion planets could potentially support life as we know it, we're still left with 200 trillion potentially habitable worlds. That's more potentially life-bearing planets than there are stars in our entire Milky Way galaxy. This statistical reality is what drives modern astronomers and astrobiologists to pursue what was once considered pure science fiction. The numbers alone suggest that the universe should be teeming with life. Yet, as we look around our cosmic neighborhood, we see silence. This apparent contradiction between the statistical probability of life and the lack of evidence for it is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" But before we can tackle that profound question, we need to understand how we're actually finding these distant worlds, and what we're learning about them. The story of exoplanet discovery is one of human ingenuity, technological innovation, and the relentless pursuit of knowledge that defines our species at its best. The search for exoplanets began not with sophisticated space telescopes, but with patient astronomers using ground-based instruments to detect the subtle gravitational dance between stars and their planetary companions. It's a story that began with theoretical predictions and has evolved into one of the most exciting fields of modern astronomy. The Great Exoplanet Revolution, how we find worlds beyond our solar system. For centuries, we knew of only one planetary system, our own. The idea that other stars might host planets was purely theoretical, relegated to the realm of philosophy and science fiction. But in 1995, everything changed. Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Eridani b, the first confirmed exoplanet orbiting a sun-like star. This discovery didn't just add one more world to our cosmic catalog. It opened the floodgates to an entirely new era of astronomy. The method they used was elegant in its simplicity, yet incredibly challenging to execute. They employed what's called the radial velocity method, also known as the wobble technique. Here's how it works. When a planet orbits a star, it doesn't just orbit around a stationary point. Both the star and the planet orbit around their common center of mass, called the barycenter. From our perspective on Earth, this causes the star to wobble slightly back and forth. This wobble is incredibly tiny. We're talking about movements measured in meters per second, comparable to the speed of a leisurely walk. But these minute movements cause detectable changes in the star's light spectrum through the Doppler effect. As the star moves toward us, its light shifts slightly toward the blue end of the spectrum, and as it moves away, it shifts toward the red end. By measuring these tiny spectral shifts with incredible precision, astronomers can infer the presence of an orbiting planet. The discovery of 51 Eridani b was revolutionary, but it also challenged our assumptions about planetary formation. This world was a hot Jupiter, a gas giant larger than Jupiter but orbiting its star closer than Mercury orbits our Sun. According to our understanding of planetary formation, gas giants should form far from their stars where it's cold enough for ice to condense and help build massive planets. Yet here was a Jupiter-sized world completing an orbit in just over 4 days. This discovery forced astronomers to rethink planetary formation and migration. We now understand that planets can migrate inward after formation, sometimes ending up in scorching orbits that would have seemed impossible just decades ago. This realization expanded the possible types of planetary systems we might expect to find throughout the galaxy. But the radial velocity method, while groundbreaking, has limitations. It's most sensitive to large planets orbiting close to their stars, exactly the opposite of what we might expect for potentially habitable worlds. To find Earth-like planets in Earth-like orbits, astronomers needed different techniques. Enter the transit method, which has become the workhorse of exoplanet discovery. This technique relies on the occasional alignment of planetary orbits with our line of sight to their host stars. When a planet passes in front of its star as seen from Earth, it blocks a tiny fraction of the star's light, causing a measurable dimming. For an Earth-sized planet crossing a Sun-like star, this dimming amounts to just 0.01%, equivalent to detecting the shadow of a coin passing in front of a car headlight from several miles away. The precision required for transit detection pushed telescope technology to its absolute limits. Ground-based telescopes could detect the larger signals from gas giants, but finding Earth-sized planets required the steady, unblinking eye of space-based observatories. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of planetary populations by staring at a single patch of sky containing about 150,000 stars for nearly 4 years. Kepler's discoveries were nothing short of astounding. It found planets ranging from scorching hot super-Earths to frozen gas giants, from worlds with diamond rain to planets orbiting double star systems like something out of Star Wars. But perhaps most importantly, Kepler showed us that small, rocky planets are incredibly common in our galaxy. One of Kepler's most significant contributions was revealing the abundance of super-Earths, planets larger than Earth but smaller than Neptune. These worlds, which don't exist in our solar system, appear to be among the most common types of planets in the galaxy. This discovery forced us to reconsider whether our solar system is typical or unusual in its architecture. The transit method also opened up new possibilities for studying exoplanet atmospheres. When a planet transits its star, some of the star's light passes through the planet's atmosphere before reaching us. Different gases in the atmosphere absorb specific wavelengths of light, creating a unique spectral fingerprint. By comparing the star's spectrum during and outside of transit, astronomers can determine the atmospheric composition of distant worlds. This atmospheric analysis has revealed some truly bizarre worlds. We've found planets where it rains molten glass sideways due to supersonic winds, worlds covered in lava oceans, and gas giants with atmospheric temperatures exceeding 2,000 degrees Celsius. Each discovery adds another piece to our understanding of planetary diversity and helps us appreciate just how special, or perhaps how typical, our own world might be. But the search for exoplanets isn't just about cataloging cosmic real estate. Each discovery brings us one step closer to answering fundamental questions about life's prevalence in the universe. As we've developed more sophisticated detection methods and launched more advanced telescopes, we've begun focusing our attention on a very specific type of world, those that might be capable of supporting liquid water and potentially life as we know it. The Goldilocks zone, searching for just right. In the classic fairy tale, Goldilocks finds that Papa Bear's porridge is too hot, Mama Bear's porridge is too cold, but Baby Bear's porridge is just right. This simple concept has become central to our search for potentially habitable exoplanets. Astronomers use the term Goldilocks zone, or habitable zone, to describe the region around a star where conditions might be just right for liquid water to exist on a planet's surface. The concept seems straightforward enough, not too close to the star where water would boil away, not too far where it would freeze solid, but right in that sweet spot where oceans could persist. For our solar system, Earth sits comfortably in the habitable zone, while Venus is too hot and Mars is too cold. But as we've learned more about exoplanets, and even the worlds in our own cosmic neighborhood, we've discovered that the reality of habitability is far more complex and nuanced than this simple temperature-based definition suggests. The habitable zone's position and width depend entirely on the host star's properties. Massive, hot stars have habitable zones that are much farther out and wider than those around smaller, cooler stars. A red dwarf star, which makes up about 75% of all stars in our galaxy, has a habitable zone that's very close to the star, so close that planets within it would be tidally locked, with one side permanently facing the star and the other side in eternal darkness. This tidal locking creates its own set of challenges for habitability. The day side of such a planet might reach temperatures of several hundred degrees, while the night side could be frozen solid. However, recent climate models suggest that thick atmospheres could potentially redistribute heat around the planet, creating a more temperate environment. Some scientists even speculate that the boundary region between the day and night sides, the terminator zone, could provide stable conditions for liquid water and potentially life. The atmospheric composition of a planet plays a crucial role in determining its actual surface temperature, sometimes overriding the simple distance-based habitable zone calculation. Venus, for example, sits closer to the habitable zone's inner edge in our solar system, but its thick carbon dioxide atmosphere creates a runaway greenhouse effect that makes its surface hot enough to melt lead. Conversely, early Mars likely had a thicker atmosphere that kept liquid water stable on its surface despite being at the outer edge of the habitable zone. This is where the search for exoplanet atmospheres becomes critical to understanding habitability. The James Webb Space Telescope, with its unprecedented infrared capabilities, is beginning to analyze the atmospheric compositions of potentially habitable exoplanets. By detecting the spectral signatures of water vapor, carbon dioxide, methane, and other gases, we can start to piece together whether a distant world might actually be hospitable to life. One of the most intriguing exoplanetary systems discovered to date is TRAPPIST-1, located about 40 light-years away in the constellation Aquarius. This system contains 7 Earth-sized planets orbiting a red dwarf star, and at least 3 of these worlds sit within the habitable zone. What makes TRAPPIST-1 so fascinating is that its planets are packed incredibly tightly together, the entire system would fit within Mercury's orbit around our Sun. The TRAPPIST-1 planets are in a complex gravitational dance called orbital resonance, where their orbital periods are related by simple ratios. This resonance helps stabilize the system and provides clues about how the planets formed and migrated to their current positions. Initial atmospheric studies have begun for some of these worlds, with early results suggesting that at least some may lack the thick, steamy atmospheres that would make them uninhabitable. But what excites researchers most about systems like TRAPPIST-1 is the possibility of conducting comparative planetology across multiple worlds in the same system. By studying how different planets and identical stellar environments evolved, we can better understand the factors that make worlds habitable or hostile to life. The search for habitable exoplanets has also forced us to expand our definition of where life might exist. In our own solar system, we've discovered that some of the most promising locations for finding life aren't on the surfaces of planets at all, but in the subsurface oceans of icy moons like Europa, Enceladus, and Titan. These worlds receive energy not from their parent star, but from tidal heating caused by their gravitational interactions with their giant planet hosts. This realization has opened up an entirely new category of potentially habitable worlds, those with subsurface oceans maintained by tidal heating or radioactive decay rather than stellar radiation. Such worlds could exist far beyond the traditional habitable zone and might be incredibly common throughout the galaxy. Large moons of gas giant exoplanets, which we're just beginning to detect, could harbor vast hidden oceans beneath their icy surfaces. The complexity of habitability extends beyond just temperature and liquid water. A planet's magnetic field, which protects its atmosphere from being stripped away by stellar wind, plays a crucial role in long-term habitability. The rotation rate affects climate patterns and atmospheric circulation. The planet's size determines how long it can maintain geological activity, which helps regulate atmospheric composition through volcanic outgassing and plate tectonics. Even the planet's position within its stellar system matters in ways we're still discovering. Recent studies suggest that gas giant planets in the outer reaches of a system can act as vacuum cleaners, using their gravity to prevent asteroids and comets from bombarding inner planets. Jupiter likely plays this protective role for Earth, though some impacts are beneficial for delivering water and organic compounds necessary for life. As we refine our understanding of habitability, we're developing increasingly sophisticated models that take into account dozens of factors beyond simple distance from the host star. These models help guide our observational priorities, focusing our limited telescope time on the most promising targets for follow-up atmospheric studies. The next phase of exoplanet research will focus intensively on atmospheric characterization of potentially habitable worlds. We're looking for biosignatures, chemical indicators that could only be produced by living processes. But identifying these signatures from light years away presents some of the most challenging technical problems in all of astronomy. The hunt for life, biosignatures across the cosmic void. Imagine trying to analyze the contents of a glass of water from across a football stadium while someone shines a powerful spotlight directly into your eyes. This analogy barely captures the technical challenge facing astronomers as they attempt to detect signs of life in the atmospheres of distant exoplanets. We're trying to analyze incredibly faint chemical signatures in the thin atmospheric shells of worlds separated from us by trillions of miles, all while their host stars outshine them by factors of billions. Yet despite these seemingly impossible odds, we're making remarkable progress in developing the tools and techniques necessary to search for biosignatures, chemical indicators that could reveal the presence of life on distant worlds. This search represents perhaps the most profound scientific endeavor in human history, the attempt to determine whether life exists beyond Earth. The most obvious biosignature would be oxygen, or more specifically, the combination of oxygen and water vapor in a planet's atmosphere. On Earth, Oxygen is a highly reactive gas that would quickly disappear from our atmosphere if it weren't constantly replenished by photosynthesis. Free oxygen in the presence of water vapor creates a strong indication of active biological processes, since no known geological process can maintain high oxygen levels over long periods. However, detecting oxygen in exoplanet atmospheres is extraordinarily difficult. Oxygen absorbs light most strongly in the infrared part of the spectrum, but even then, the signal is incredibly weak. The James Webb Space Telescope represents our best current hope for detecting oxygen in the atmospheres of nearby potentially habitable exoplanets. But even this remarkable instrument will require multiple observations of the same planet to build up enough signal to confidently detect this biosignature. Methane presents another promising biosignature, particularly when found in combination with oxygen. On Earth, methane is constantly produced by biological processes ranging from bacterial metabolism to cow digestion. Like oxygen, methane is chemically reactive and would quickly disappear from an atmosphere unless constantly replenished. Finding methane and oxygen together would be especially compelling, since these gases react with each other and can only coexist if both are being actively produced. But the search for biosignatures is complicated by the fact that many potentially biological signatures can also be produced by non-biological processes. Methane, for example, can be generated by volcanic activity or chemical reactions in a planet's interior. Oxygen can be produced by the photodissociation of water molecules in a planet's upper atmosphere, though this process typically creates only small amounts compared to biological production. This is where the power of spectroscopy becomes crucial. By analyzing not just the presence of these gases but their relative abundances and how they vary over time, astronomers can begin to distinguish between biological and non-biological sources. A planet with large amounts of oxygen but no accompanying water vapor might indicate photodissociation rather than photosynthesis. Seasonal variations in atmospheric composition could reveal biological cycles, similar to how Earth's atmospheric carbon dioxide levels fluctuate with the growing seasons. Beyond these obvious biosignatures, astronomers are considering more subtle indicators that might reveal the presence of life. Phosphine, recently detected in Venus's atmosphere, is another gas that breaks down quickly in the presence of oxygen and is primarily produced by biological processes on Earth. Industrial pollutants like nitrogen dioxide or chlorofluorocarbons could indicate not just life, but technological civilization, though detecting such trace gases would be far beyond our current capabilities. Some researchers are even considering more exotic biosignatures that might indicate forms of life unlike anything on Earth. Purple bacteria, which use different light-harvesting pigments than green plants, might create a distinctive spectral signature called the red edge that could be detectable on exoplanets. Unusual ratios of atmospheric gases, even if each individual gas could be produced by geological processes, might collectively point to biological activity. The challenge of false positives, non-biological processes that mimic biosignatures, is one of the most serious obstacles in the search for life. Young, active stars can drive complex atmospheric chemistry on their planets through intense ultraviolet radiation. Volcanic activity can produce many of the same gases associated with life. Even the process of planetary formation and evolution can create atmospheric compositions that might initially appear biological. This is why atmospheric studies of potentially habitable exoplanets require not just detection of interesting gases, but detailed characterization of entire atmospheric systems. We need to understand a planet's atmospheric pressure, temperature profile, cloud composition, and weather patterns to distinguish between biological and non-biological explanations for unusual chemistry. Current and future space telescopes are being designed with these challenges in mind. The James Webb Space Telescope can analyze the atmospheres of some large, hot exoplanets by observing them during transit, when their atmospheres are backlit by their host stars. Future missions like the proposed HabEx or LUVOIR space telescopes would be capable of directly imaging potentially habitable exoplanets and analyzing their atmospheric spectra without waiting for fortuitous transit alignments. Ground-based telescopes are also contributing to this effort. The new generation of extremely large telescopes, with mirrors 30 meters or more in diameter, will have the light-gathering power and resolution necessary to study the atmospheres of some nearby exoplanets. These telescopes will use advanced techniques like stellar coronagraphy to block out the overwhelming light of host stars and reveal the faint light reflected from their orbiting planets. But perhaps the most exciting prospect for biosignature detection lies in the combination of multiple observations and techniques. By studying the same potentially habitable planet with different instruments, at different wavelengths, and over multiple time periods, astronomers can build up a comprehensive picture of its atmospheric composition and behavior. This multifaceted approach will be essential for making the extraordinary claim that we've detected signs of life beyond Earth. The statistical approach to biosignature detection is equally important. As we discover and characterize hundreds or thousands of potentially habitable exoplanets, patterns may emerge that help us distinguish between biological and non-biological atmospheric compositions. Even if we can't definitively prove that any single planet hosts life, the statistical distribution of atmospheric types across many worlds could provide compelling evidence for the prevalence or rarity of life in our galaxy. Recent advances in machine learning and artificial intelligence are also being applied to the biosignature detection problem. These tools can analyze vast amounts of spectroscopic data and identify subtle patterns that might be missed by human researchers. As our datasets grow larger and more complex, AI may play an increasingly important role in sifting through the noise to find genuine signals of life. The implications of successfully detecting biosignatures go far beyond just adding another discovery to our catalog of exoplanet properties. Such a detection would represent the first confirmed evidence that life exists beyond Earth, a discovery that would fundamentally change our understanding of our place in the universe and the prevalence of life in the cosmos. But what if, despite our best efforts and most sophisticated instruments, we continue to find sterile worlds? What if the galaxy is full of potentially habitable planets that remain stubbornly lifeless? This possibility brings us to one of the most profound questions in all of science, the Fermi paradox and the haunting possibility that we might be alone after all. The Great Silence, confronting the Fermi paradox. On a summer evening in 1950, physicist Enrico Fermi was walking to lunch with colleagues at Los Alamos National Laboratory when their conversation turned to a recent spate of UFO sightings. After discussing the topic with his characteristic scientific rigor, Fermi suddenly stopped and asked a question that would echo through the halls of science for decades. Where is everybody? This simple question encapsulates what has become known as the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations existing in our galaxy and the complete absence of evidence for such civilizations. Given the vast number of stars, the abundance of planets we're discovering, and the immense age of the universe, it seems almost inevitable that intelligent life should have arisen many times and in many places. Yet when we look out into the cosmos, we see nothing but silence. Let's examine the numbers that make this paradox so compelling. Our Milky Way galaxy contains approximately 100 billion stars, and we now know that most of these stars host planetary systems. Even conservative estimates suggest that billions of planets in our galaxy alone might be capable of supporting liquid water. Given that life appeared on Earth relatively quickly after conditions became suitable, and that intelligence eventually evolved here, it seems reasonable to expect that similar processes might occur elsewhere. Furthermore, Our galaxy is ancient by cosmic standards, about 13.6 billion years old, compared to Earth's 4.5 billion years. This means there has been ample time for intelligent civilizations to arise, develop technology, and spread throughout the galaxy. If just one civilization had developed interstellar travel and decided to colonize other worlds, they could theoretically spread throughout the entire galaxy in just a few million years, a blink of an eye in cosmic terms. Yet when we scan the skies with our most sensitive instruments, we detect no artificial signals, no evidence of massive engineering projects, no signs of industrial activity on other worlds. The galaxy appears to be remarkably quiet, at least at the frequencies and with the methods we're currently using to listen. This silence has profound implications for our search for life. If advanced technological civilizations were common, we might expect to see evidence of their activities long before we develop the capability to detect simple biosignatures in exoplanet atmospheres. The fact that we don't see such evidence suggests several possible explanations, each with disturbing implications for humanity's future and our place in the cosmic order. One possibility is the Great Filter hypothesis, proposed by economist Robin Hanson. This idea suggests that there's some stage in the evolution from simple matter to space-faring civilization that is extremely unlikely to overcome. This filter could lie in our past, perhaps the transition from non-living matter to self-replicating life, or from simple cells to complex organisms, or from animal life to intelligence is far more difficult than we imagine. If the Great Filter lies behind us, then we are extraordinarily fortunate to have made it this far, and simple life might be much rarer in the universe than our optimistic calculations suggest. This would explain why we don't see evidence of other civilizations. They simply don't exist in significant numbers because the crucial evolutionary steps that led to our existence are vanishingly rare. Alternatively, the Great Filter might lie ahead of us. Perhaps intelligent civilizations inevitably develop technologies that lead to their own destruction before they can spread beyond their home planets. Nuclear weapons, climate change, artificial intelligence, biotechnology, or other existential risks might consistently eliminate civilizations before they become detectable to distant observers. This explanation is particularly unsettling because it suggests that humanity may face the same fate that has befallen countless other intelligent species. Another category of explanations focuses on the behavior and motivations of advanced civilizations. Perhaps intelligent species typically choose not to expand throughout the galaxy, finding it more efficient or desirable to focus their development inward rather than outward. Advanced civilizations might prefer to build sophisticated virtual realities, upload their consciousness to computers, or explore inner space rather than outer space. Some researchers have proposed that truly advanced civilizations might be virtually undetectable to us because their technology operates on principles we don't understand or using energy sources that don't produce the signatures we're looking for. They might have moved beyond chemical rockets and radio telescopes to technologies based on physics we haven't discovered yet. The zoo hypothesis suggests that advanced civilizations are aware of us but have chosen not to make contact, either to avoid interfering with our natural development, or because they find us uninteresting. Like researchers observing animals in a nature preserve, they might maintain a respectful distance while studying our progress. This idea is philosophically troubling because it places humanity in the role of primitive subjects being observed by vastly superior intelligences. Recent developments in our understanding of exoplanets have added new dimensions to the Fermi paradox. The discovery that red dwarf stars, which make up about 75% of all stars, have habitable zones where planets would be tidally locked has raised questions about whether such worlds can actually support complex life. The high-energy radiation from young red dwarfs might strip away planetary atmospheres, sterilizing potentially habitable worlds before life can gain a foothold. Similarly, Our growing understanding of the importance of plate tectonics, magnetic fields, and large moons in maintaining planetary habitability suggests that truly Earth-like conditions might be rarer than initially thought. Perhaps the convergence of factors that made Earth suitable for complex life represents such an unlikely combination of circumstances that we are indeed alone in our galaxy, if not the universe. The temporal aspect of the Fermi paradox is equally puzzling. Even if civilizations are relatively rare, the galaxy has existed for over 13 billion years, enough time for numerous cycles of stellar formation, planetary development, and potential biological evolution. Where are the traces of ancient civilizations? Shouldn't we see archaeological evidence of species that rose and fell billions of years before Earth even formed? Some scientists have proposed that we might actually be seeing evidence of cosmic engineering, but we're misinterpreting it as natural phenomena. Unusual astronomical objects like fast radio bursts, gamma-ray bursts, or even structures like Tabby's star, which showed bizarre and unexplained dimming patterns, have been suggested as possible artifacts of advanced technology. However, natural explanations have been found for most of these phenomena, and the search for genuinely artificial signatures continues. The Fermi paradox also raises questions about the nature of intelligence and consciousness themselves. Perhaps what we consider intelligence is not as universal or inevitable as we assume. Human intelligence emerged through a specific evolutionary pathway shaped by our particular environment and evolutionary pressures. Other forms of intelligence might develop along completely different lines, making them unrecognizable to us or incapable of the kind of technological development that leads to space exploration. Recent research in astrobiology has revealed that Earth's history includes several near-extinction events that could have prevented the evolution of complex life. The Great Oxygenation event about 2.4 billion years ago poisoned most existing life forms, but enabled the evolution of complex organisms. Multiple mass extinctions have shaped the course of evolution on our planet, and it's possible that similar events on other worlds might consistently prevent the development of advanced life forms. The search for extraterrestrial intelligence continues despite the apparent silence. Projects like SETI scan the skies for artificial signals, while researchers study anomalous astronomical objects for signs of technology. The Breakthrough Listen initiative is conducting the most comprehensive search for extraterrestrial intelligence in history, monitoring millions of stars across a wide range of frequencies. As we continue our search for exoplanets and signs of life, the Fermi paradox serves as a sobering reminder that the universe might be far stranger and more hostile to life than our optimistic expectations suggest. Whether we're alone by circumstance, by choice of others, or by the fundamental nature of cosmic evolution itself, the question remains one of the most profound challenges facing human science and philosophy. Life beyond our imagination, expanding the definition of habitable. When we search for life in the universe, we naturally begin with what we know, life as it exists on Earth. We look for liquid water, moderate temperatures, and chemical signatures that match the biological processes we observe in our own biosphere. But this Earth-centric approach might be limiting our ability to recognize life that evolved under completely different conditions and follows entirely different rules of chemistry and physics. The history of life on our own planet suggests that biology is far more creative and adaptable than we initially imagined. Every time scientists have declared certain environments completely hostile to life, we've discovered organisms thriving in precisely those conditions. From the crushing depths of oceanic trenches to the boiling hot springs of Yellowstone, from the highly acidic volcanic vents to the extremely salty Dead Sea, life has found ways to not just survive but flourish in conditions that would instantly kill most familiar organisms. These extremophiles, as they're called, have fundamentally changed our understanding of life's possibilities. Thermophiles thrive in temperatures exceeding 80 degrees Celsius, while psychrophiles prefer temperatures below freezing. Acidophiles flourish in environments more acidic than battery acid, and alkalophiles prefer conditions more basic than household bleach. Some organisms, called polyextremophiles, can tolerate multiple extreme conditions simultaneously. Perhaps most remarkably, we've discovered life forms that don't depend on photosynthesis or organic compounds for energy. Deep in Earth's crust, miles below the surface, communities of microorganisms survive by extracting energy from radioactive decay or chemical reactions with rock minerals. These chemosynthetic ecosystems could potentially exist on worlds throughout the galaxy, completely independent of stellar radiation. This discovery has revolutionary implications for astrobiology. If life can exist miles beneath Earth's surface, sustained by geological rather than astronomical energy sources, then potentially habitable zones extend far beyond the narrow bands around stars where liquid water can exist on planetary surfaces. Rocky planets and large moons throughout a stellar system might harbor vast underground biospheres that we wouldn't detect with conventional atmospheric analysis. The moons of Jupiter and Saturn have become prime targets for astrobiology precisely because of this expanded understanding of habitability. Europa, Enceladus, and Titan all show evidence of subsurface oceans that could contain more liquid water than all of Earth's oceans combined. These hidden seas, warmed by tidal heating and possibly enriched with organic compounds, might provide ideal conditions for life to emerge and evolve. Recent studies of Earth's deep biosphere have revealed that subsurface life might actually represent the majority of biomass on our planet. If this pattern holds elsewhere, then most life in the universe might exist in hidden underground environments that we're only just beginning to learn how to detect and study. But expanding our definition of habitability goes beyond just considering different environments. We must also consider different types of chemistry. All life on Earth is based on carbon chemistry in liquid water, but this might not be the only possible foundation for biology. Silicon, which sits directly below carbon on the periodic table, shares many of carbon's chemical properties and could potentially form the backbone of alternative biochemistries. Silicon-based life might thrive at much higher temperatures than carbon-based organisms, potentially existing in environments like the surfaces of Venus or the hot atmospheres of gas giants. However, silicon biochemistry would face significant challenges, as silicon compounds tend to be less stable and versatile than their carbon counterparts. Nevertheless, we shouldn't dismiss the possibility entirely, especially in environments where carbon-based life couldn't survive. Alternative solvents present another avenue for exotic life forms. While we focus our search on liquid water, other liquids might serve as the medium for biological processes. Liquid ammonia, which remains liquid at much lower temperatures than water, could potentially support life on cold worlds far from their host stars. Methane, which exists in liquid form on Saturn's moon Titan, might also serve as a biological solvent, enabling completely different types of chemical reactions and metabolism. The discovery of life forms on Earth that use arsenic in place of phosphorus in their DNA structure, though this finding remains controversial, hints at the possibility that the fundamental building blocks of life might be more flexible than previously thought. If organisms can substitute one element for another in such a crucial biological molecule, then life might be capable of even more radical chemical innovations on other worlds. Energy sources for exotic life forms could be equally diverse. While photosynthesis and chemosynthesis dominate Earth's biosphere, other forms of metabolism might exist elsewhere. Some theoretical biologists have proposed that life could potentially derive energy from magnetic fields, gravitational gradients, or even the quantum vacuum itself. These energy sources might seem exotic to us, but they represent vast, untapped reservoirs of power that could sustain biological processes under the right conditions. The time scales of exotic life forms might also differ dramatically from what we observe on Earth. While terrestrial organisms operate on time scales ranging from microseconds to centuries, hypothetical life forms based on different chemistry or existing in different environments might function over geological time scales. Such organisms might be virtually undetectable to us because their biological processes occur too slowly for us to recognize as signs of life. Conversely, some forms of life might operate at extremely rapid time scales, perhaps based on quantum mechanical processes or high-temperature chemistry. These organisms might complete entire life cycles in fractions of a second, making them equally difficult to detect with current observational methods designed to study processes occurring over human-comprehensible time periods. The implications of exotic life forms for our search strategies are profound. Current biosignature detection methods are based on the assumption that extraterrestrial life will produce chemical signatures similar to those created by terrestrial organisms. But if life elsewhere follows completely different chemical pathways, uses alternative solvents, or operates on vastly different time scales, we might be looking for entirely the wrong signals. This challenge is compounded by our limited understanding of how exotic biochemistries might manifest themselves in planetary atmospheres or surface compositions. While we know that oxygen and methane are produced by Earth life, we have no idea what gases might be produced by silicon-based organisms living in liquid ammonia, or what surface features might indicate the presence of subsurface ecosystems based on entirely different principles. Some researchers have proposed that we should look for more general signatures of biological activity, patterns that might indicate the presence of complex, self-organizing systems regardless of their specific chemistry. These might include unusual isotope ratios, complex organic molecules, or atmospheric compositions that are far from chemical equilibrium. Such signatures might be detectable even if the underlying biology is completely unlike anything on Earth. The search for technosignatures, evidence of technological activity rather than biological processes, might be even more promising for detecting exotic forms of intelligence. Advanced civilizations, regardless of their biological origins, might engage in large-scale engineering projects or use technologies that produce detectable signatures across interstellar distances. These could include artificial structures around stars, unusually regular patterns of radio or optical signals, or modifications to planetary atmospheres that couldn't occur naturally. Recent advances in our understanding of quantum biology, the role of quantum mechanical effects in biological processes, have opened up entirely new possibilities for exotic life forms. Quantum coherence plays important roles in photosynthesis, bird navigation, and possibly even consciousness itself. Life forms that evolved in different environments might exploit quantum effects to a much greater degree, potentially enabling biological processes that seem impossible according to classical physics. Imagine organisms that exist in quantum superposition states, processing information through quantum entanglement, or deriving energy from quantum field fluctuations. Such life forms would be so alien to our experience that we might not recognize them as living even if we encountered them directly. They might exist as distributed quantum fields rather than discrete physical entities, communicate through mechanisms we can't detect, or manipulate matter and energy in ways that appear supernatural to us. The possibility of digital life forms, self-replicating patterns of information rather than chemistry, has gained serious consideration as our own technology becomes increasingly sophisticated. If intelligence can arise from sufficiently complex information processing systems, then digital organisms might evolve within the computational substrates created by technological civilizations. These digital life forms could potentially outlast their biological creators, spreading through communication networks and existing as pure information. Such digital organisms might be completely invisible to our current search methods, which focus on detecting chemical signatures or physical artifacts. They could inhabit the computational networks of advanced civilizations, spread through interstellar communication systems, or even exist within the quantum computational processes of the universe itself. The implications of these expanded possibilities are both exciting and humbling. They suggest that the universe might be teeming with forms of life and intelligence so alien to our experience that we lack the conceptual framework even to imagine them, much less detect them. Our search for extraterrestrial life might be like a fish trying to detect the presence of birds. We're looking in the wrong medium, at the wrong scales, and for the wrong types of activity. This realization has led some researchers to advocate for a much broader approach to astrobiology, one that doesn't just look for Earth-like life on Earth-like planets, but actively seeks out the weird, the unexpected, and the seemingly impossible. This approach requires us to question our fundamental assumptions about what life is, how it operates, and where it can exist. At the same time, we must balance this expanded vision with practical constraints. Our current technological capabilities limit us to detecting certain types of signals and signatures. While we should remain open to discovering exotic forms of life, we must also focus our limited resources on searches that have a reasonable chance of success with existing or near-future technology. The search for conventional biosignatures in the atmospheres of potentially habitable exoplanets remains our most promising near-term strategy for detecting extraterrestrial life. Even if exotic life forms are common throughout the universe, finding any form of life beyond Earth would represent a profound breakthrough that would revolutionize our understanding of biology, evolution, and our place in the cosmos. The psychology of discovery, what finding life would mean for humanity. As we stand on the precipice of potentially discovering life beyond Earth, it's worth considering not just the scientific implications of such a discovery, but the profound psychological, philosophical, and cultural impact it would have on our species. The confirmation that we are not alone in the universe would represent perhaps the most significant paradigm shift in human history, comparable to the Copernican revolution that displaced Earth from the center of the cosmos, but with implications that reach far deeper into the human psyche. Throughout recorded history, humans have oscillated between feeling cosmically significant and cosmically insignificant. Ancient cultures placed Earth at the center of creation, with humans as the pinnacle of divine intention. The scientific revolution gradually eroded this anthropocentric view, revealing our planet to be one of many worlds orbiting an ordinary star in an unremarkable galaxy among billions of others. Yet even as our cosmic status diminished, we retained one claim to uniqueness. We appeared to be the only known bearers of life and consciousness in the universe. The discovery of even microbial life beyond Earth would shatter this last bastion of human exceptionalism. Suddenly, we would no longer be the universe's only known experiment in biology, but merely one example among potentially countless others. This shift in perspective would likely trigger a range of psychological responses across different individuals and cultures, from profound wonder and excitement to existential anxiety and fear. For some, the confirmation that life exists elsewhere would validate long-held beliefs and fulfill deep-seated hopes about our cosmic neighborhood. The sense of isolation that has haunted human consciousness since we first comprehended the vastness of space would be replaced by a comforting knowledge that we are part of a larger community of living worlds. The universe would suddenly seem less empty, less hostile, and more like a home capable of nurturing life in multiple forms. Religious and spiritual communities would face particular challenges in integrating the reality of extraterrestrial life with existing belief systems. Some faiths might find the discovery entirely compatible with their teachings, seeing it as evidence of the divine creative force operating throughout the cosmos. Others might struggle to reconcile the existence of alien life with doctrines that place humans in a special relationship with the divine. The discovery could also trigger a renaissance of philosophical inquiry into fundamental questions about consciousness, intelligence, and the meaning of existence. If life arose independently on multiple worlds, it would suggest that the emergence of biology, and possibly intelligence, might be a natural and perhaps inevitable outcome of cosmic evolution rather than an extremely unlikely accident. This realization could profoundly affect how we view our own existence and our responsibilities as conscious beings. The type of life discovered would significantly influence humanity's psychological response. Finding simple microbial life would be scientifically revolutionary but might have a relatively modest impact on daily human concerns. Most people might acknowledge the discovery as important while continuing to focus on immediate terrestrial issues. However, the detection of complex, intelligent life would likely trigger much more dramatic psychological and social responses. Evidence of technological civilizations would raise immediate questions about their capabilities, intentions, and potential impact on human civilization. Even if these civilizations existed thousands of light years away, making direct contact impossible with current technology, their mere existence would force us to reconsider fundamental assumptions about intelligence, technology, and social organization. The discovery of more advanced civilizations could trigger what psychologists call an inferiority complex on a species-wide scale. Humans pride themselves on being the most intelligent species on Earth, but confronting evidence of vastly superior alien intelligence might challenge our collective self-esteem and sense of accomplishment. Some individuals might respond with wonder and curiosity, eager to learn from more advanced beings, while others might feel threatened or inadequate. Conversely, discovering less technologically advanced civilizations might reinforce human confidence but would raise profound ethical questions about our responsibilities toward other intelligent species. The history of human contact between technologically disparate cultures provides sobering lessons about the potential consequences of such encounters, even when they occur across interstellar distances. The timeline of discovery would also influence human psychological responses. A gradual accumulation of evidence over many years would allow society to slowly adjust to the new reality, while a sudden, undeniable revelation would likely cause more dramatic disruption. The way the discovery is communicated to the public, through careful scientific announcements or sensationalized media coverage, would significantly affect how people process and respond to the information. Different cultures and societies would likely interpret the discovery of extraterrestrial life through their own unique lenses of history, values, and worldview. Western scientific cultures might focus primarily on the research opportunities and technological implications, while indigenous cultures with strong connections to natural systems might view alien life as part of an extended cosmic ecology. Societies with histories of colonization might worry about alien conquest, while others might hope for beneficial contact and knowledge exchange. The economic implications of discovering extraterrestrial life could be enormous, potentially triggering new industries, research programs, and international cooperation efforts. Space exploration budgets might increase dramatically as governments and private organizations rush to study newly discovered life forms or search for ways to communicate with intelligent civilizations. The mere possibility of learning advanced technologies from alien sources might justify massive investments in SETI research and interstellar communication projects. Educational systems would need to fundamentally restructure their approaches to teaching biology, astronomy, and philosophy. The discovery of life beyond Earth would necessitate new curricula that help students understand their place in a universe teeming with biology rather than the seemingly sterile cosmos we currently inhabit. This educational shift could have profound long-term effects on how future generations view themselves and their responsibilities. The discovery might also catalyze a new sense of global unity among humans. Confronted with evidence that we are not alone, national, ethnic, and religious differences might seem less significant compared to our shared identity as terrestrial life forms. This could potentially reduce conflicts and promote cooperation, though history suggests that humans are equally capable of finding new sources of division even in the face of common challenges or identities. However, the psychological impact wouldn't be uniformly positive. Some individuals might experience what could be called cosmic anxiety, a deep unease about humanity's place in a universe that suddenly seems much more complex and potentially threatening. The comfortable illusion of human centrality and cosmic significance would be permanently shattered, potentially triggering existential crises for some people. There might also be concerns about the implications for human uniqueness and individual worth. If intelligence and consciousness can arise naturally throughout the universe, what makes human thoughts, emotions, and experiences special? This question might lead some people to nihilistic conclusions, while others might find it liberating to be part of a larger cosmic community of conscious beings. The discovery of extraterrestrial life would also raise immediate questions about protection and preservation. If we found microbial life on nearby worlds, we would face ethical obligations to protect these organisms from contamination by Earth life. The realization that we might inadvertently be destroying alien ecosystems through our space exploration activities would likely trigger new international protocols for planetary protection. For the scientific community, the discovery would mark the beginning of entirely new fields of study. Astrobiology would transform from a largely theoretical discipline to an empirical science with actual alien organisms to study. New subfields would emerge focusing on alien biochemistry, evolutionary biology, and comparative planetology. The discovery would also validate decades of investment in astrobiology research and likely lead to massive increases in funding for related studies. The search continues, current missions and future prospects. Right now, as you're watching this video, multiple spacecraft are hurtling through space on missions that could answer the fundamental question of whether we're alone in the universe. These robotic explorers represent humanity's most ambitious attempt to find evidence of life beyond Earth, and their discoveries in the coming years could fundamentally change our understanding of our place in the cosmos. The James Webb Space Telescope, which began operations in 2022, is already revolutionizing our ability to study exoplanet atmospheres. This remarkable instrument can detect the chemical signatures of distant worlds by analyzing the light that passes through their atmospheres during transit events. Webb's infrared capabilities allow it to study atmospheric compositions with unprecedented precision, potentially revealing the presence of water vapor, carbon dioxide, methane, and other gases that could indicate biological activity. Recent observations from Webb have already provided tantalizing glimpses of exoplanet atmospheres, revealing complex chemical compositions and weather patterns on distant worlds. The telescope has studied hot gas giants, detecting unexpected molecules and atmospheric dynamics that challenge our models of planetary formation and evolution. As Webb turns its attention to smaller, more temperate worlds, we may be approaching the moment when we detect our first potential biosignature in an exoplanet atmosphere. But Webb is just the beginning. The European Space Agency's Plato mission, scheduled to launch in 2026, will search for Earth-like planets orbiting Sun-like stars. Unlike previous missions that focused on nearby red dwarf systems, Plato will look for worlds that more closely resemble Earth in terms of their stellar environment. These planets would receive similar amounts of radiation to Earth and would be more likely to maintain stable, temperate climates suitable for life as we know it. NASA's Nancy Grace Roman Space Telescope, launching in the mid-2020s, will use gravitational microlensing to detect exoplanets throughout our galaxy, including free-floating planets that have been ejected from their star systems. This technique could reveal a hidden population of rogue worlds drifting through interstellar space, some of which might retain enough internal heat to support subsurface oceans and potentially life. Even more ambitious projects are on the drawing boards. The proposed Habitable Exoplanet Observatory, HabEx, would be capable of directly imaging potentially habitable exoplanets and analyzing their atmospheric spectra. Unlike transit observations that require fortunate alignments, direct imaging would allow us to study many more worlds and characterize their properties in much greater detail. HabEx could potentially detect oxygen, water vapor, and other biosignatures in the atmospheres of dozens of nearby potentially habitable planets. The Large UV/Optical/IR Surveyor, LUVOIR, concept represents an even more ambitious vision, a space telescope with a segmented mirror up to 15 meters in diameter that could directly image and characterize potentially habitable exoplanets around hundreds of nearby stars. LUVOIR would have the sensitivity to detect atmospheric biosignatures even in the presence of clouds and weather patterns that might obscure signals from less capable instruments. Ground-based astronomy is also contributing to the search through the construction of extremely large telescopes. The 30-meter telescope, the Giant Magellan Telescope, and the extremely large telescope will have mirrors so large and sensitive that they can study the atmospheres of some nearby exoplanets directly. These telescopes will use advanced adaptive optic systems to compensate for atmospheric turbulence, and sophisticated coronagraphs to block out the overwhelming light of host stars. But the search for life isn't limited to distant exoplanets. Several missions are currently exploring potentially habitable environments much closer to home, within our own solar system. NASA's Perseverance rover is actively searching for signs of ancient life on Mars, drilling into rocks that formed in environments that could have supported microbial organisms. The samples it's collecting will eventually be returned to Earth for detailed analysis that could reveal definitive evidence of past or present Martian life. The upcoming Dragonfly mission will send a nuclear-powered helicopter to explore Titan, Saturn's largest moon. Titan's thick atmosphere and lakes of liquid methane create a unique environment that could support exotic forms of life based on entirely different chemistry than terrestrial organisms. Dragonfly will analyze Titan's surface composition and atmospheric chemistry, looking for signs of biological activity that might be invisible to Earth-based observations. Europa Clipper, scheduled to launch in 2024, will conduct detailed studies of Jupiter's moon Europa, which likely harbors a subsurface ocean containing more liquid water than all of Earth's oceans combined. The mission will map Europa's surface, analyze its thin atmosphere, and use ground-penetrating radar to study the structure of its ice shell and underlying ocean. While Europa Clipper won't land on the surface, it will determine whether Europa's ocean could support life and identify the best locations for future missions that might directly sample the subsurface sea. These solar system missions are crucial to astrobiology because they could provide our first definitive detection of extraterrestrial life, even if it's only microbial. Finding life anywhere beyond Earth would prove that biology is not unique to our planet, and would provide crucial insights into how life arises and evolves under different conditions. The search for extraterrestrial intelligence continues through projects like Breakthrough Listen, which is conducting the most comprehensive search for technosignatures in history. Using some of the world's largest radio telescopes, Breakthrough Listen monitors millions of stars across a wide range of frequencies, looking for artificial signals that could indicate the presence of technological civilizations. Recent advances in signal processing and machine learning are enhancing our ability to sift through vast amounts of data from SETI searches. AI algorithms can identify patterns that might be missed by human researchers and can process much larger datasets than was previously possible. As our computational capabilities continue to improve, we may be able to detect increasingly subtle signals that could reveal the presence of alien technology. The next decade promises to be particularly exciting for astrobiology. Multiple missions will be returning samples from Mars, analyzing the atmospheres of potentially habitable exoplanets, and exploring the subsurface oceans of icy moons. For the first time in human history, we have the technological capability to seriously search for life beyond Earth across multiple fronts simultaneously. But perhaps most importantly, we're developing the theoretical framework and analytical techniques necessary to recognize life when we find it, even if it's dramatically different from terrestrial biology. This combination of improved technology and deeper understanding of life's possibilities gives us unprecedented opportunities to answer one of humanity's most profound questions. The question isn't really whether we'll find life beyond Earth. Given the vastness of the universe and the apparent abundance of potentially habitable environments, it seems almost inevitable that life exists elsewhere. The real questions are when we'll find it, what form it will take, and how that discovery will change our understanding of ourselves and our place in the cosmos. A cosmic perspective, what the search means for humanity. As we reach the end of our journey through the cosmos of exoplanets and the search for life, it's worth stepping back to consider what this entire endeavor means for us as human beings. The search for life beyond Earth is ultimately a search for understanding our own nature and place in the universe. Every exoplanet we discover, every atmospheric spectrum we analyze, every biosignature we seek, brings us closer to answering fundamental questions about the nature of existence itself. Carl Sagan once described Earth as a pale blue dot, a tiny, fragile world suspended in a vast cosmic arena. This perspective, gained from our exploration of space, has profound implications for how we view ourselves and our responsibilities. When we search for other pale blue dots orbiting distant stars, we're not just conducting scientific research. We're expanding our cosmic consciousness and developing a deeper appreciation for the rarity and preciousness of life wherever it occurs. The search for exoplanets has already revealed that planetary systems are incredibly diverse and common throughout our galaxy. This discovery alone has transformed our understanding of cosmic architecture and our place within it. We now know that our solar system is just one example among billions of possible configurations of worlds orbiting stars. Some systems have multiple gas giants packed closer together than Mercury orbits our Sun. Others have super-Earths in tight orbits around red dwarf stars. Still others have planets orbiting binary star systems, creating alien skies illuminated by two suns. This diversity suggests that the universe is far more creative and dynamic than we ever imagined. Each new type of planetary system we discover expands our understanding of the possible, and challenges our assumptions about what's normal or typical in cosmic terms. This expanding perspective naturally leads us to wonder what other forms of complexity and organization might exist on scales we haven't yet explored. The search for biosignatures forces us to think deeply about the nature of life itself. What is it that makes something alive rather than just a complex chemical system? How do we distinguish between biological and non-biological processes operating on distant worlds? These questions push us to refine our understanding of the fundamental principles that govern living systems and to consider possibilities that stretch far beyond our terrestrial experience. Even if we never detect definitive evidence of extraterrestrial life, the search itself has tremendous value. It drives technological innovation, pushes the boundaries of human knowledge, and inspires new generations of scientists and explorers. The instruments we develop to study exoplanet atmospheres often find applications in Earth observation, climate monitoring, and other fields that directly benefit human society. The search also fosters international cooperation and peaceful collaboration. Astronomy is one of the few human endeavors that naturally transcends national boundaries and political divisions. When we study distant stars and planets, we're engaging in a fundamentally human activity that unites us across cultures and civilizations. The data we collect belongs to all humanity, and the discoveries we make expand the knowledge and wonder available to every person on Earth. There's something profoundly hopeful about the search for extraterrestrial life. It represents an optimistic bet that the universe is full of interesting, complex, beautiful phenomena waiting to be discovered. It assumes that intelligence and consciousness are valuable and worth seeking out wherever they might exist. It demonstrates humanity's willingness to invest enormous resources and effort in pursuing knowledge that might have no immediate practical benefit, but could transform our understanding of reality itself. The psychological impact of the search may be as important as any discoveries we make. By seriously contemplating the possibility that we're not alone, we're preparing ourselves psychologically for what could be the most important discovery in human history. We're developing the intellectual and emotional frameworks necessary to process such a revelation if and when it comes. Whether we find simple microbes in the subsurface oceans of Europa, detect biosignatures in the atmosphere of a distant super-Earth, or receive a radio signal from an advanced technological civilization, the discovery of extraterrestrial life would mark a new chapter in human history. It would validate our scientific methods, confirm our deepest intuitions about the nature of the universe, and provide new directions for research, exploration, and philosophical contemplation that could occupy our species for millennia to come. But even the absence of detectable life would tell us something profound about the universe and our place in it. If we search thoroughly and find nothing, it would suggest that life, consciousness, and intelligence are far rarer and more precious than we currently imagine. This discovery would place enormous responsibility on humanity as potentially the only known bearers of consciousness in a vast, unconscious cosmos. The search for exoplanets and extraterrestrial life represents humanity at its best: curious, persistent, collaborative, and willing to ask profound questions even when the answers might be uncomfortable or challenging. It demonstrates our species' remarkable ability to transcend immediate survival concerns and pursue knowledge for its own sake. As we continue this cosmic quest, we're not just looking for other worlds and other forms of life. We're exploring the deepest questions about existence, consciousness, and meaning that have puzzled humans since we first developed the capacity for abstract thought. We're using the most sophisticated tools and techniques our civilization has ever developed to probe the ultimate mysteries of nature. And regardless of what we find, or don't find, in our search, the journey itself is transforming us. Every time we discover a new type of exoplanet, analyze another atmospheric spectrum, or detect another potentially habitable world, we're expanding our cosmic perspective and deepening our appreciation for the complexity and beauty of the universe we inhabit. The hunt for exoplanets and the search for life beyond Earth will likely continue for as long as human civilization exists. It represents one of our species' most noble aspirations: to understand our place in the cosmos and to discover whether we share this vast universe with other forms of life and consciousness. So the next time you look up at the stars, remember that some of those tiny points of light are now known to host worlds that might be very much like our own. And remember that right now, telescopes and spacecraft are actively studying those distant worlds, searching for signs that we are not alone in this magnificent cosmic arena we call home. The universe is vast, full of possibilities, and waiting to share its secrets with those brave enough to search. Whether we're alone or part of a vast community of living worlds, the search itself enriches our understanding and expands our sense of wonder about the incredible cosmos we're privileged to explore. What do you think we'll find out there among the stars? Are you ready for the possibility that within your lifetime, we might finally answer the question that has haunted humanity since the dawn of consciousness? Are we alone? Share your thoughts in the comments below. I'd love to know what you think about our place in this vast cosmic ocean, and what it would mean to discover that we're not the only ones calling it home. The search continues, and the greatest discoveries may still lie ahead.